Okay, AP Calculus BC, Unit 4, Day 3 lesson. So say we've spent the last couple lessons, days, working on just kind of figuring out what polar curves look like, how to graph them. And so now we're going to start to bring in some of the calculus. I mean, none of that was really calculus yet. Just, I mean, as far as like, we teach it in calculus, but we could teach polar coordinates in other courses probably too. But now we're going to bring in derivatives and integrals, and that's really where we're going to bring calculus into this. So just quick review. I guess we could do a quick sketch of this graph. You guys should hopefully be getting to the point now where you recognize that this is a cardioid. And so we just plug these values in. Cosine 0 is 1, so it's going to be 0, 1, 2, 1, 0. Should look kind of sideways, horizontal in orientation. Could probably make, let's say, 1, 2, 3, 4. We'll try and make this graph bigger. So I'm going to make 4 of these marks equal to one unit. And so quick sketch 0, 0, pi over 2, 1, pi 2, 3 pi over 2, 1, 2 pi 0. So it's going to kind of look like this. And they're very round, and have this cusp right here. So just a quick sketch. This is where it started and ended, and this is the directions going on. The directions I think can actually be important in this. Now, first of all, if we look at dy dx, it's the rate of change of y with respect to x, and it's really just change y over change x like we've always thought of it. And so we can look at this graph and say, okay, well, there's this whole section right here where if you're to draw like a tangent line, dy dx would be positive for that whole chunk from here to here. And then right here, dy dx would be 0, it would be flat, right? Here, dy dx would be undefined because it's infinitely steep, division by 0. We'd have another dy dx equals 0 over here. We'd have another vertical tangent, dy dx equals undefined. Have another one right here, dy dx equals undefined. Now, in this whole chunk right here, dy dx is going to be negative slopes here from here to here. Now, right here, I think we'll probably say that dy dx equals 0 at that cusp. And then, but from here to here, this little chunk, that's going to be dy dx is positive slopes here to here. Dy dx is negative from here to here. Dy dx is positive. If you just draw a tangent line, it has a positive slope here to here. Dy dx is negative. So just looking at it and drawing some slopes, you can kind of see what dy dx is doing, or it's positive, negative, 0, undefined. And that's just kind of what we've always thought of the slope of a curve. I mean, this is a weird curve I haven't seen before, but we can just draw tangent lines. Now, drd theta is going to be the rate of change of r, the radius, right? The radius with respect to theta, the angle. So that means is if r is getting bigger as the angle is getting bigger, then that's a positive drd theta. If the radius is getting smaller as theta gets bigger, that's negative. If they're both, so if we look at this graph at first, the radius is for sure getting bigger, all the way to here, right? As theta is getting bigger. So this whole chunk right here, dr d theta is positive. And at this point right here, or dy dx is undefined, dr d theta equals 0, because this is the point where the radius now starts to get smaller. So for this whole chunk, dr d theta is negative because the radius is getting smaller and smaller and closer to the pole as theta gets 0. So that's how the radius is changed with respect to theta. Now, we can write some formulas, which I'm going to tell you not to use. I'm going to go ahead and write them down because you're going to see them in your textbook, and I want you to know that I talked about them, but I'm going to be very against them. Now, dr d theta, r is usually written with respect to theta. For instance, here's an example that we're going to use. Okay. And so taking the derivative of r with respect to theta, it's just kind of like a regular derivative. That's like r prime theta. And we might write it, you might refer to it more generically as some function with theta involved in it. For this specific example, it would just be sine theta. So there's no formula to memorize there. You're just taking the derivative of r with respect to the variable that's in it. Now, trying to figure out dy d theta and dx d theta and dy dx, that's a little more challenging. Okay. Now, it's going to start with x equals r cosine theta and y equals r sine theta. These relationships between rectangular and Cartesian coordinates and polar coordinates. Now, for this specific example, you would just plug in the equation for r. And so you could plug that in for r, and now you have equations for x and y in terms of theta. So now you could find dy d theta. You can take the derivative of x with respect to theta and derivative of y with respect to theta, just using basic derivative rules. Now in the book, they're gonna kind of take this approach. Well, r is actually some function f, or they might put r in there, and they say, well, this right here, this is r, which is f, so we got to do let's see. If we're doing dy d theta, this one right here, we'd say, well, here, this is r, right? Some function. And so we got to do product rules, what they're saying. The derivative sine is cosine. And then, product rule, we got to do that times derivative of that. So that's going to be the derivative of f times sine theta. Okay. Or we could write in terms of r. And so that's just using the product rule, on this relationship. Okay. And we can do the same thing for x. We say, okay, well, that's r, so we're going to do f theta times derivative cosine is negative sine. And then we're going to do the derivative of f times cosine. Or you could write it with r, so you could say r, negative r sine theta plus r prime cosine theta. But here's the deal. I'm going to say, you know what? Let's not use these at all. I mean, it's totally unnecessary, because what you're going to do is you're going to write this, which you're really good at anyways, what you need to be good at for other things. And if you want the derivative of y, well, why don't you just take the derivative of that? And you could do product rule. You could say, okay, well, it's going to be 1 minus cosine theta times derivative of sine is cosine theta plus, sine theta times the derivative of that's going to be sine theta. Just get your answer that way. Like, why do you need this formula that's based off this really basic derivative rule that you learned at the beginning of Calc AB? You don't. Do not use these. Okay? If you do, one, you're making it harder for yourself right away. Two, if you mess up, I'm going to grade it so badly. I'm going to complain even if you pull it off right. Okay? You got to think long term. End of the year, when you have all these different formulas, remember, you really want to add this stuff to it when it's totally avoidable. So derivative of x for this specific example, because that's what you're going to do. You're just going to just find the x and y equations. That's something you should already know how to do, and then take the derivative of it. So I mean, it's quicker, I think, than trying to follow this formula. I mean, this formula just kind of represents the pattern that we're always going to use, but do not use them. I don't want to see them on any of your homework. Now, dy dx, it's kind of interesting. This is kind of like parametrics. The way we find dy dx is we do dy d theta over dx d theta. So it's kind of like a um, it's kind of like a chain rule issue, right? So we could say, well, dy dx, we could take the derivative of y with respect to theta because that's what we have it in terms of, but then we got to take the derivative of theta with respect to x because that's what we want the final derivative in terms of. So it's this chain rule where you got to take the derivative of what's inside afterwards. Now, if we manipulate this, we get dy d theta over dx d theta, right? So I think that's kind of easy to remember, and that's all you need to know. You could then, if you look in the book, they take these formulas and they plug them into this formula, which is, I'm going to write it down, but I don't want to see anyone ever use it. But I want you to know that I showed you and I talked about it, and I want you to know that I never want to see you use it. So dy d theta has to be on top, and then dx d theta would be on the bottom. So you could do that, or you can put it in terms of r cosine theta plus r prime sine theta over negative r sine theta plus r prime cosine theta. But never, ever, ever use these. It's dumb. It's just dumb. This is the one thing you need to know. And this is the one thing you need to know. And after that, if you just combine those two things, you can do these problems. And these formulas aren't going to save any time. They're going to probably add time and you're going to mess them up. So in this case right here, I would find dy d theta first and dy dx d theta, and then I'd put them together. I mean, you might even just do them both at the same time. So, anyways, the only thing, like I said, do not use these. The only thing to remember is this, which you already know, and this, which is new, but is just like something from parametric. So that should feel dy dx from parametrics was dy dt over dx dt. So we'll do one example on the back without using the formulas. And the book assignment is slightly different than what I have on the sheet. So you want to, I'll go ahead and correct that right now. I cut out some of the work. So we're going to do number 1, parts A and B only. So it cuts out half of that problem. Problem 3, parts A and B only. I'm going to do 6 to 10 all. So I took out one of those problems. And then we're going to do 21 to 27 odd. So I took another one of those problems out. And then we're going to do 39 to 41. And you can kind of skip the last ones. So this is the assignment. So takes out a little bit of the work. Check your odds. Most of them are odds. Most of them are in the back of the book. And so let's try this example right here. Now here's the thing I'm going to suggest. This is the thing I'm going to recommend, that you draw a quick sketch of this, because the sketch is going to make it really kind of obvious what dy dx should be. It should be positive, negative, super steep, not super steep, 0, undefined. And it's easy to make little mistakes in this work with a positive or negative. But if you have a sketch, then you're going to be able to catch that mistake. And I think these sketches are going to be really helpful. And you should be getting pretty good at them. So this is a cardioid, right? And we can do a quick table. Theta is going to be horizontal in orientation. I mean, you guys should be getting pretty quick at these. So this is going to give you some extra practice on this anyway. So that's going to be 0, 1, 2, 1, 0. So quick sketch. It's going to be bigger in the left direction. So just quick sketch. This isn't, and sometimes they might give you actual sketches already on the homework, which is nice. But so 0, 0, pi over 2, 1, pi 2, 3 pi over 2, 1. So the graph looks like that. That's it. Quick sketch. Now we're asking for the dy dx at pi over 3, which is kind of like right here. So it looks like it might be vertical, or it might be, it looks pretty steep negative, but maybe it's like, it's hard to tell, like, because that depends on how good you drew the picture. But I think if it came out vertical, undefined, that doesn't seem horrible. If it came out positive, that seems a little weird to me. If it came out like flat, probably wrong. So let's write down our equations. X equals r cosine theta. So that's going to be 1 minus cosine theta, and y equals r sine theta. So it's going to be 1 minus cosine theta, sine theta. And I usually just leave it like this. I'm going to do product rule. You're not going to avoid product rule. You're going to have to do it anyways, or chain rule and stuff like that. So I usually just leave it like this. And then, if you feel comfortable, I think you could jump down to dy dx and do dy d theta on top. So 1 minus cosine theta times 0 of sine is cosine plus sine times 0 of that's going to be sine, right? And then on the bottom, it's going to be dx d theta. So it's going to be 1 minus cosine theta times 0 of cosine is negative sine plus cosine theta times sine theta. There you go. No formulas. That's it. Now, if you felt, if you felt better about it, you could do dy d theta and dx d theta separate first, and then put them together. And then maybe sometimes there's a reason to do them separate, anyways. In that case, great. But I felt pretty good about just jumping right into it if you want to save time. Otherwise, if you feel like you need to be a little more careful, you could do the separate first. And then you can do this one. Then you could put them into the fraction. Now, I would definitely write it down. And then we're going to plug pi over 3 in. And then that's when, gets a little tedious. So, I think I'm going to start doing it in my head. Okay, so cosine of pi over 3 is 1/2. So 1 minus 1/2 is 1/2. And then it's going to be 1/2. And then sine of pi over 3 is root 3 over 2, root 3 over 2, root 3 over 2. You can show more work in between. And this is going to be another 1/2 times negative root 3 over 2 plus 1/2 root 3 over 2. And now we're just going to clean it up. So that's going to be, a nice trick would be to multiply the top and bottom by 4 to get rid of all the fractions, right? Get rid of those, and get rid of those. So then you would just have a 1 plus 3 on the top over negative root 3 plus root 3 on the bottom, and that would give you 4 over 0, which would give you undefined, which totally makes sense with my picture. So that's the new kind of stuff. Tonight's homework has a little bit of practice from stuff from the last couple days, and then you do get to try some of these. So try them out, check your odds, and then we'll do some more stuff with derivatives later.